please don't do that. I handcrafted them lovely in my garage. Don't ruin them for me. But if you were to unfold them, that's what the sides look like. You know the average is 8.17 and the standard deviation is the 2.65. Of course, you don't know that because that's the population value, right? So what I did was I redid your quiz that you just did using Excel. Does this graph look familiar right here? Does this graph look kind of familiar from before? If it doesn't, that's okay. Does it look like that? Hopefully. Look at the shape here. Bar's a little wider, but no big deal. Now, what's cool about this is dynamic, which means what I'm doing right now as I'm pressing F9 is I'm rolling those dice and I'm keeping track of every result that I get in that graph. See how it's changing each time? But is it changing very far from the population's distribution? No, it's dancing around it. It's dancing around it, okay? I did one more thing too. I changed these to percentage of occurrence or probability. Just I'm a bastard. We'll come back to that too. Okay? Fair enough? But again, this is fiction. This is assuming you're actually getting your population. So, I then decided to simulate your quiz. Now, this is the same thing you guys did, except I did it, I think, 1,000 or 10,000 times. I can't remember how many times. It's a lot. So remember how that blue curve that you guys had up here in your results looked really good? Here's your blue curve right there. We said, oh, it's kind of a bell shape. Here's what happens if you do the experiment a few thousand more times. Do you think it looks more like a bell shape than the one you guys got? Well, yeah, because you got a lot more data, so all those little goofy holes are going to fill in. All those goofy little gaps are going to fill in over time. Can you see where the average is? Can you see? Watch the dance. Watch the dance of 10,000 rolls at a time. You see where the average is showing up? Where? Who wants to come up and point to it? Come up and point to where the highest bar usually is. Or use a laser pointer. We have no laser pointer.
I got a quick question.
Zach, go!
You got like 5.5, 6.5, as opposed to we didn't have the 0.5s, did we?
Oh, you could have had it. You could have had it if you got 6.677. That averages a 6.5. You can't have anything more precise than 0.25. You could have 0.75s, 0.5s, or whole numbers. It depends on what numbers you got. Is that fair?
Mm-hmm. Is that as far as what we did, our graphs compared
Oh, I'm sorry. Let me come back to that question. Where I'm graphing it. The reason is because there's so much more data. I wanted to break it up and make it more fine-toothed comb, if that makes sense. And I want to come back to that. I instituted this guy right here last term because of that exact question. So hold that thought if you don't mind. Zach's question is, when you look at my horizontal right here, I've got it broken up in half-unit increments versus whole unit, only because I got a lot more data and it fills out the graph nicer with more. And we'll go even further than that. Okay, good enough? So do you guys see where mu is? Hopefully. It's right around that highest point of the curve. It's bouncing quite a bit. Okay, I decided to try it again, but I used a sample size of 9 instead. Not 4, but 9. So, can you find the average now of that? Do you notice the bell curve is back? Yes, the bell curve is there, yes. Can you find the average where it roughly is? Yes? Watch the dance, watch the dance. You see how we're getting that highest spike? Now you know from cheating that the average is about an 8.2. Is the highest spike indicating where that average is? On average over time? Yes, it is. How is this curve n equals 4 different than n equals 9? There's n equals 9. Here's n equals 4. What's the difference? They're both bell curves. Both bell curves are sitting on top of the average. So what's the difference?
Wider.
Wait, say that again.
Wider.
Which one's wider?
4.
This is the 4, right? This is no, the 9. Sure, 4's here. Look at the 4s where the tails are. The most extreme tails are showing up down here. Look at 9. Where are his most extreme tails showing up? We're not getting any ones down here. Why aren't we getting any ones down there? Why aren't we getting anything down here now?
When you divide by 9, that's all.
When you think about it, you're repeating the experiment 9 times before averaging, right? In order to land down here, you have to get those extreme values over and over and over again. Is that easy or hard?
Hard.
It's hard to do because it shouldn't happen very often, which makes it an outlier, which puts it off the chart. Boom! It's just like everything we've been talking about. If it's hard to do, you're not going to see it very often. Every once in a blue moon you will. You'll see a little blue bar go, boop. But you have to run this thing like 1,000,000 times to see it. So I decided to do one better. Sample size of 16. 16. 16 now, 16. How is it like all the other curves we've seen so far? The average is exactly the same. Beautiful. The average is exactly the same. Did you catch this? This bar is always the tallest. The one that contains the average is always the tallest one. Have you been watching the numbers on this vertical axis over here? That's the probability of that bar. That bar probability keeps getting higher and higher and higher. Because why? Why are we getting more and more likely to land in that bar? Think about what we just said about 30 seconds ago.
Sample size gets bigger, so it's compressing and going up.
Yes! You know that 100% of what happens has to land in this curve. If it's getting harder and harder to land out here, where does all that area have to go? Or here, for that matter. If it's harder and harder to land here, where must it be getting easier and easier to land? So in other words, you're compressing the curve like this, and that means the middle of the curve has to be going like that to make up for it. It has to. It has to be 100% in total. It has to be 100% in total. So if we're losing the tails, we have to be gaining the middle. Good news for us. Let's keep going. Let's go to a sample size of 25. Still a bell curve, as Jen said, still focused on the average, even tighter than 100, yeah? Or even tighter than 16. Then I jump to 100.
Wow.
Now this is slick. I like this one a lot. I like this one a lot because there really is no doubt in my mind where the average is anymore. I mean, that bar's not even really moving all that much. And I mean, look, 62% of the time we're getting data that's within 0.3 or 0.2 of the average. But Zach, what I decided to do was, some students look at that and go, I don't even see a bell curve anymore. So watch this. What I did was I took that same result and made the horizontal axis even more fine-toothed. So in other words, what you're seeing right now on that axis is everything. See how it starts at 7? That is that right here. And then if you look at this one, the high end out here goes out to 9.5. That is this guy right here. So if you took this to this, cut everything else out and stretched it out, that would look like this, which is a gorgeous little bell curve. Again, it's like a micro view of the macro, if that makes sense. So that's what the more trials, the more precision you can get in your result. But again, where's the average? I think it's right there. And it dances around, but on average it is right there. Now what's happening to the curves as the sample sizes get bigger? I love this. This is my favorite. I always see this. Week 10, class 2, what happens to the curves? They do this. I love this. And what else do they do? This and good, or that. I like that. I usually see this. But this and this. They get narrower and tighter. What does that mean about the sample standard deviations of these curves? They're getting smaller. So, my last thing I want you to realize is this. This is a little bit to look at first. What this is it's all 5 of those spreadsheets I just showed you in one place. Now, as you press F9, see the bottom down there? Those are all the histograms you just looked at, but they're all in the same set of axes. So, Jen, we're seeing this and this as you go front to back. This front curve here is your quiz. This front curve is your quiz, the one you guys just did, if you had blue dice. The next curve back was a sample size of 9. The next curve back was a sample size of 16, 25, and then 100. Notice how they're getting narrower and taller. It looks like the ocean, I know. It's kind of fun. I love using the blue on that because it looks kind of like the ocean. Now, here's your sample sizes listed up here. Here are the averages that we were getting in the spreadsheet. Please take a look. What are those numbers all hovering right around, friends? What are those numbers all hovering right around? They're all hovering right around the population mean that you will never know. So do you need to know it? No, because your sample is going to tell it to you. This is the point of statistics. What you're seeing right here is the next foot into 244. You're never going to get to know that your sample mean is 8.1666666 repeated. Because you can't measure your entire population. But look at these sample averages you're getting. They're all hovering right around 8.1666 repeating, which means you don't have to know what mu is if you get a good look at mu. And look, it's consistent. Sometimes they're high, sometimes they're low, but they're always on average hitting it. Ha! That's exciting, to me at least. Maybe not to you, it's okay. It's a nice day outside when you get out of it. I appreciate that. But this is exciting statistically, because you don't have to know mu to be able to get mu. Now, a concern you might have as statisticians, I would have this concern, is, yeah, but when you're in this curve down here, yeah, this is the tallest bar, the one that contains 8.2, which is the average. The problem is, it's like saying, oh, we should play craps, because rolling 7 is the highest roll, and when you get paid out when you roll 7. But not rolling 7 is way more likely than rolling 7. Just like not landing in this bar is way more likely than landing in this bar. Until your sample size goes through the roof, and all of a sudden that bar becomes the most likely outcome, because the curves are tightening down. So now I want to answer the question that I posed to you guys a few moments ago, which is how these numbers, or in particular right now, that number, plays into these graphs. So here are the standard deviations of each of these curves. Say that again.
The bigger the sample size, the smaller the standard deviation.
The bigger the sample size gets, the smaller the standard deviation. Can anybody tell me predictably how much smaller it gets? In other words, look at these numbers here. You might be wondering why I chose these numbers. Just figure it out right now. Here's the population standard deviation, about 2.7, roughly 2.7. How are these numbers compared to 2.7? What's this one compared to 2.7?
It's double plus 1.
It's about a half, isn't it? Say that again. Double.
I was trying to figure out.
Hold that thought. Oh, I know what you're saying, Zach. This is about half, isn't it? What's this one? Ish. Half of the first one? It's a little bit. I'd say it's about 50% less than the first one, which would be a third of this one. Right? If you think about it, call that 0.9, round up to the 10th place. 0.9, 2.7, that's about a third. And again, they're going to bounce around. They're not perfect. But you see how that's hovering around 0.9? It's about, okay? How's this guy compared to this one? Ish. Roughly. You know what? Here, let me do something easier. Let me do this divided by this value, except I have to actually type it in. G3 divided by 2.69. Here, I'll just do this. And then we'll just do this. Okay? So there's some numbers for us to look at. So what is this fraction right here hovering around? We just said about a half. What's this number hovering around right here? 0.33 is about a third, isn't it? What's this one hovering around right here? A fourth. What's this one hovering around right here? A fifth. What's this one hovering around right here? Careful! It's tempting to go to 6, but it's actually a 10. A half, a third, a fourth, a fifth, a 10th. Is there a pattern there? Is there a pattern there? What's the pattern? What's the pattern? A half. 4.
Yes.
A third. Say it. You know it. It's math 65. This is a bastard move on the last day of class.
It's 50% of 4, and then the next one.
Square root of the sample size. Check it out. A half, 2. Square root of 4 is 2. A third, 3, 1 over 3. Square root of 9 is 3. A fourth, 4. Square root of 16. You wonder why I pick these weird numbers. I'm picking perfect squares to make the math easy. I tried. I tried to make a sample size of 10,000. So this would be 0.01. And the problem, I found Excel's limit. You can fill up Excel with too much crap. I pressed the F9 button and went, and like 36 seconds later it went, and I'm like, they will never accept that in class. They won't sit here for 52 minutes while I reload this thing 10 times. So I wanted to go, but you could predictably know what it was. That's the point about predictability. If this were 10,000, which is not that big a sample by like FDA standards, this would be 0.01. Which means there's almost no variability in your average in your sample distribution, which means every time you run a sample, you're getting wicked close to the average you're looking for. Why does this make us happy? Because you could say, well, I am 95% confident. Say that again. Linda, go. Why does it make me happy?
Because on average.
Because on average over time, you're hitting what you're looking to hit. You're not going like this. You're going like this. Larger samples mean higher precision. Let's put it all together. You guys you just discovered everything you needed to discover. Jen, I love where you were going with it. You were looking just at this, and I love that.
Yeah. No,
It's actually a progression. It is a progression. 1/2, 1/3. It's called a harmonic series.
Oh yeah, I was just saying like 4 divided in half.
Exactly. And there's that. I think Zach was going the same place. And there is a neat relationship in there too, but there's a much simpler one. It's just square root of the sample size. Now, I'm going to put some symbols up here. This is going to be posted for you for later. The only reason I'm doing this is it's going to help you answer about 10 or 15 points on your exam. There's one question on your exam that deals with everything we're talking about right now, and I want to make sure you hear it before you have to do it. That's the whole point of this quiz, was to get you to put your... How many of you guys have taken 244 at some point? Yeah, exactly. This is the beginning right here, technically speaking. Drawing samples. So, check with Amy first. Yes, I'm kidding. So, here's the point. Don't write this down unless you want to. Unless you want to. And I'm going to have it posted for you. This will be posted for you on the schedule page, hopefully as soon as we get done class in like 5 minutes.